Hi, I'm Phil, and today we're going to look at motors for robots. So this is session 4 in the course of Robots for Seniors, and we'll look at some of my experiences using all of these motors. So the objectives are to understand the principles of rotary motion of a motor, to relate these to the electrical power, show how I use electric motors in robot projects, and demonstrate designs of mechanical and electrical properties of robots. So we go back to physics, back to first principles, and we have a look at torque. So we can get a feel when we have a spanner and a nut, and the force we're applying there is an angular movement as we turn the screw or the nut. So in our fundamentals, we look at force, and we start off with a linear motion just by pushing an object on the surface, and that force that we push it with equals mass times acceleration. And torque is the equivalent angular movement, and it is measured in Newton meters. So torque equals force times distance, and that distance is the moment of the arm. And power that we use to do all that, if it's coming from a battery or a electrical power supply, it's current times voltage. And the power in the mechanical world is torque times angular velocity. And if we relate these to electrical parameters, the motor efficiency is the mechanical power over the electrical power. And mechanical power is torque times angular velocity, and the electrical power includes the mechanical power plus the heat losses in the resistance of the motor coil. And that equals I squared R. I being current, and R is the resistance of the coil. And if we represented a DC motor with a diagram, an electrical diagram, we have on the left the battery and the resistance of the coil. L is the inductance of the winding, and that produces the magnetic field. The small e is the back EMF, and we have a fixed coil interacting with the current produced by the field windings. Okay, I've got quite a number of motors, and I've compared them all on this table. So all the motors starting from the top I use for a drone, right down to the bottom one, which is the most powerful one. And I've rated these according to torque. If the manufacturer provides it, I use that. And the motor that we're using on our course is the KittenBot Geek Servo 2 kilogram motor, and it's about halfway down. So it's a good compromise in terms of cost and performance. And the torque that I'll be using is on the right column. And the units for that are Newton meters. The only one that I have a bit of doubt about is the SG90 servo. It just seems a little bit high on the high end, but we might actually do some measurements of that later on. Okay, so we start off with the one with the weakest torque, and that's a brushless motor, the 1503. What's interesting about brushless DC motors is that they have a wide range, and they're used in very high speed applications like drones, but they can also be wound in a way that gives a lot more torque than this particular motor. The torque on this one is low, but the speed is normally very, very high, and it's used in drone applications. The next motor we're increasing in torque value is the roller can unit from M5 Stack. And again, it's a brushless DC motor. And these are the characteristics of it. And the torque is shown here on the list. And I use that for projects like this one, where I'm moving in the both. I've got two axes. I've got the horizontal and the vertical axis, where I'm moving a camera with pan and tilt. And I've also used it with the Seed Studio AI rear camera, where in this case I'm only moving it in the pan direction. And a typical low power motor that comes from Zoom is the 310 encoder DC motor. And you get these in low cost robot kits. And normally you don't select the robot motor. It's already selected for you. And the torque on that one is we're beginning to increase in our torque value. So we're almost just under 0.05 Newton meters for this one. And that's used in the robot car. And this robot car uses a Raspberry Pi. It's one of the lowest costs that come from Boom. And the one that we could use on our project, it's completely Lego compatible from KittenBot. It uses the 9-gram motor, and the torque on that is similar to the one that I showed previously. But there's no encoder on this one. And the torque on that one you can see on the diagram. And here's an example where I've used that and how it mounts with Lego components with a microbit computer. Another very popular DC motor is the TT motor that has a gearbox. And you can get this with both encoder or without the encoder. And we're beginning to increase in our torque value here, 0.15 Newton meters. And often when you're quoted the value, it's the stalled torque. So it stalls on 0.6 and there's no speed at that. And that's used in robot projects such as the JetBot smart car. NVIDIA Jetson Nano computer is used for that, and it's supplied by Seed Studio. It's also used in the Mate Block MBot robot, and together with line following and range sensors, you can build a small robot like this in a few minutes. It uses a computer on the M-Core board, which is Arduino Uno compatible. And you can do your software development either with MateBlock or with the Arduino IDE. So here's a breakaway diagram of the robot, and we can see where the M-Core computer is near the top, and on the bottom we have our motors. And on the next diagram we can see the electrical connections on how both the sensors and the motors are assembled on the MBot computer. And here's another diagram with the ports illustrated. Another popular robot in Europe, particularly in Germany, comes from Fisher Techniques, and one of their projects is the fan control using their small X. And the motor used here is the XS motor, and it includes a gearbox. And the project that I'm going to show here is using the microbit and the Kintronic microbit interface board for Fisher Technique electronics. And it's also going to use a thermistor in the fan control and an LED. And this is what it looks like when it's assembled. And here it is on my desktop. From Lego, we've got a lot of motors. And this particular one here is called the M motor. And it's a range of motors were available from Lego. The only ones that are available now are the spike ones on the bottom right. But you can still pick up some of the other ones, like the power functions medium one, which we're illustrating here. And there's also the power functions XL robot. So the actual diagram here is for the power functions XL. And this Lego enthusiast has actually measured the power output in terms of torque. And it's the stalled torque that we're talking about here in Newton centimeters. And you can put this on projects, low-cost projects. So this is an MOC design, which is copying a lot of the Lego Technique components, and for a low cost of around about $41 from AliExpress, you can put together a small robot project. And this is also capable of being computer controlled. A similar project is the motorized evacuator, excavator, and it's just under $49. And the M motor, you can see the characteristics of it here at different voltage from 4.5 volts to 12 volts. The lowest voltage is the least energy efficient. It's only 22%, whereas if you get it up to 12 volts, you can get the efficiency up to 40%. And we can also plot the torque versus speed in RPM. And here you can see on the extreme right on the rotation speed curve, the maximum torque is around about 11 Newton meters, and the maximum torque, you can see that around about 11, and that's the pink curve. The blue curve is the speed curve. And we can also have a look at the power versus torque. So when we're doing design, having diagrams like this can help us choose the most efficient torque, or the maximum torque that we can get out of a particular motor. The one we're using on our project is the KittenBot Geek Servo 2 kilowatt motor, kilogram motor, and it has a maximum torque of 1.6, and we can translate that to 0.16 Newton meters. So it's adequate for the project that we'll be using later on. And here is that project. It's the M5 stack car, and the wheels are being driven by this particular motor arrangement. An alternative motor is to use a servo motor. In this case, it only goes through a range of 180 degrees. but it's also available in a 360 degrees for constant movement. And they quote 0.176 Newton meters for this one. And I think that's probably a little bit overrated. And that's used on projects like on the strawberry robots or the strawberry robots. And here we're combining drinking straws with servos, LEDs, a computer, and we're building a robot that can look like this. Or we can use the servo as a linear actuator, as I have done on this particular project, where we're converting the rotary movement into a linear movement. Another popular motor is the all-metal DC motor, the N20. And this is surprisingly quite small and used on quite a number of robot projects, including the DF robot micro bit robots. So you can see the torque on that. We're beginning to increase in value with 0.196 Newton meters for that one. And here it is with the DF robot McQueen Plus, and it's quite adequate for the PID control of the motors, together with additional sensors. Lego are supporting now the Lego Spike range, and this is quite powerful. So you can see the actual value on that in terms of Newton centimeters is 8 Newton centimeters, and the stalled value is 25. If we look at stepping motors, this is a stepping motor from MakeBlock, and it's used on a number of their projects, including their 3D printer, the music bot, and an XY plotter. And here is the project that I've completed on MusicBot, and it's controlled by an Arduino compatible computer. And the XY plotter looks like this. So if we go back a step up in range on the Lego, we're getting a lot more powerful. This one is 0.4 Newton meters. And again, the efficiency will increase when you increase the voltage to the motor. And again, we can have a look at the curves of torque versus speed on that one, where we've got the speed curve. It'll get up to 0 speed on the stalled position on that one. And the torque for that is 40 Newton centimeters, or 0.4 Newton meters. And we've disassembled that motor, and you can see the gears and how it's been constructed. Another popular motor that has encoders on it is the Lego EV3, the large unit on that, and we're beginning to increase in torque value. So we've got a stalled torque value of around about 43 Newton meters for that one. And that's used on their Lego EV3 robot. And this one includes the touch, the infrared ultrasonic rangefinder, and the color sensor that can be used for line tracking. And this one, we've seen the torque value, and you can reuse your Lego EV3 with the M5 stack family of components. So here on the bottom, we've got our Lego EV3 motor plugged in to a base X, M5 base X, uh, and that goes just under our M5 stack Fire computer. Alternatively, you can use an M5 stack core computer. And the Lego EV3 just plugs straight into it, and you have full motor control with encoder feedback. The final motor from Ya Boom is the 520. And this is used on their more expensive kits. So they have a kit that's about $1,500. And for this one, it's increasing the torque up to 0.431. And this is the kit that it's used on. Quite a powerful kit, although it is expensive. And here's a breakaway view of that. With you can see the motors are right on the bottom there. And going up to our most powerful motor is the Lego NXT. And this is no longer produced by Lego. They stopped making this over 10 years ago. But you can still pick them up on eBay, or you can get clones from AliExpress. And if we take this one apart, you can see the gear train. And this is one of the reasons why we've got such a powerful little motor. And it's also got encoders that help us with the position and the speed control. So again, we've got the characteristics going from low voltage and increasing in efficiency at 12 volts. You can see the power and the output of the motor. And when we compare torque with all the other Lego motors, you can see this one is quite outstanding in its output. So it's a good idea to keep this for your projects that need a little bit more power. And the rotation speed is quite the opposite. So in the design of this robot, they've increased the torque, but they've reduced the speed quite dramatically. And there's the characteristics on the torque versus speed for this motor. And here we've got some more characteristics. And here I'm using both the EV3 motors and the NXT motors with the base X motor drive from M5 stack. And this is what the base X looks like. And you can use it with NXT motors and robots. And here I've put the NXT motor onto the base X motor controller. And now I've got both of them, both the Lego EV3 motor and the Lego NXT motor, working simultaneously with the base X. And here's an example of how I'm using that on a small robot. This one has line tracking, and I'm using an AI camera. And there's another view of it with the ultrasonic rangefinder on the front.